The ocean was calm, but beneath the deck of the USS Gerald R. Ford, something terrifying was about to awaken. Two nuclear reactors armed with enough power to light an entire city came alive at once. Steam howled through miles of steel, bronze propellers began to turn, and 100,000 tons of warships shook the sea awake. This is the story of America's most powerful weapon, which just took its first breath. The USS Gerald R. Ford represents the first new aircraft carrier class designed by the United States Navy in 40 years. Construction began in 2009 at Huntington Ingalls Industries in Newport News, Virginia. The keel was laid in November 2009. First, steel had been cut in August 2005. The carrier was delivered to the Navy in May 2017 and commissioned 2 months later. The ship measures 337 meters long with a beam of 40.8 meters. Flight deck width spans 78 meters. Full load displacement reaches approximately 100,000 tons. Two Bechtel A-1B nuclear reactors power the Gerald R. Ford. Bechtel Corporation designed these reactors, marking the first time the company manufactured naval reactors despite having performed engineering or construction services on more than 80% of land-based nuclear plants in the United States. The company beat longtime naval reactor manufacturers General Electric and Westinghouse for the contract. Each A-1B reactor produces 300 megawatts of electricity. Combined output totals 600 megawatts. This represents triple the electrical generation capacity of the previous Nimitz-class carriers, which generated 200 megawatts total from their A-4W reactors. The reactor designation follows Navy nomenclature. A stands for aircraft carrier. The number 1 indicates first generation from this manufacturer. B represents Bechtel as the builder. Navy planners concluded that A-4W reactors powering Nimitz-class carriers offered insufficient power for current and anticipated future shipboard requirements. The decision to commission new reactor designs stemmed from projected demands of advanced systems, including electromagnetic aircraft launch equipment and directed energy weapons. The A-1B reactor core contains highly enriched uranium fuel. The fuel maintains sustained nuclear fission through controlled chain reactions. Neutrons released from splitting uranium atoms collide with other uranium atoms, perpetuating the reaction. Control rods made of neutron-absorbing materials regulate reaction rates. Withdrawing control rods increases power output. Inserting them reduces it. The reactor operates as a pressurized water reactor. Water circulates through the reactor core under extreme pressure, preventing it from boiling despite temperatures exceeding 500 degrees Fahrenheit. Primary coolant loops transfer heat from reactor cores to steam generators. Secondary water loops convert to steam in these generators. Steam drives turbines connected to electrical generators and propulsion machinery. The A-1B design provides 25% increase in operational availability compared to previous reactor plants. Core energy density increased significantly. Pumping power requirements decreased. Construction became simpler. Modern electronic controls and displays replaced older analog systems. The reactor plant requires 50% fewer Navy personnel for operation and maintenance compared to Nimitz-class reactor plants. Watch standing requirements decreased by 2/3. Maintenance demands dropped significantly. The modernization efforts result in $4 billion reduction in total maintenance and ownership costs per carrier over its service life. The reactors hold service lives of approximately 20 to 25 years without refueling. The carrier can operate continuously for decades, powered solely by nuclear fuel loaded during construction. 4 propeller shafts extend from the reactor plant through the hull. Each shaft connects to a 30-ton bronze propeller. The propellers measure several meters in diameter. They were installed in October 2013 during construction. The propulsion system uses turbine electric drive. Steam from reactors spins turbines. Turbines drive electrical generators. Electrical power feeds motors connected to propeller shafts. This configuration provides precise control over propulsion, superior maneuverability, and reduced mechanical complexity compared to direct mechanical drive systems. The carrier achieves maximum speeds exceeding 30 knots in ideal conditions. This equals approximately 34.5 miles per hour, or 55.5 kilometers per hour. Nuclear propulsion provides essentially unlimited travel range. The ship can reach any location connected by navigable waters that accommodate its draft. The carrier operates independently of fuel supply chains that constrain conventional vessels. No refueling stops interrupt deployment schedules. Beyond propulsion, the 600 megawatts of electrical generation capacity powers revolutionary ship systems. The electromagnetic aircraft launch system replaced traditional steam catapults used since World War II. EMALS uses linear electromagnetic motors to accelerate aircraft. Electric currents generate powerful magnetic fields. These fields propel a shuttle attached to aircraft nose gear. The system accelerates aircraft from 0 to takeoff speed within 300 feet of flight deck. EMALS launches aircraft more smoothly than steam catapults, reducing structural stress and extending airframe service lives. The system generates 25% more aircraft sorties compared to steam catapult systems. It launches heavier aircraft with greater fuel and weapons loads. The electromagnetic system requires less maintenance than hydraulic steam catapults. It occupies less internal volume, freeing space for other systems. The technology represents the first major change in carrier aircraft launch systems in 7 decades. 4 EMALS catapults installed on USS Gerald R. Ford can launch aircraft from 2 bow positions and 2 portside positions near amidships. Advanced arresting gear complements EMALS. This system uses electromagnetic technology to catch and stop landing aircraft. It replaces hydraulic arresting systems used on previous carriers. The gear weighs less than traditional systems. Software controls provide precise stopping forces matched to individual aircraft weights and landing speeds. Fewer personnel operate the system. Maintenance requirements decrease substantially. The carrier also operates electromagnetic weapons elevators. 11 advanced weapons elevators transport ordnance from magazines to aircraft on the flight deck. The elevators use linear electromagnetic motors rather than cables and pulleys. Each elevator moves 24,000 pounds of ordnance at 150 feet per minute. The system positions elevators to avoid crossing aircraft movement areas, reducing traffic congestion on hangar decks and flight decks. Centralized rearming locations streamline weapons loading operations. Previous systems required hours to rearm aircraft. The new configuration theoretically enables rearming in minutes. The massive electrical capacity reserves allow for future directed energy weapons. Laser systems require substantial, continuous power. Current systems aboard the carrier consume only 50% of total electrical generation capacity. The remaining 300 megawatts provides margin for weapons requiring megawatt-level power supplies. High-energy lasers built for point defense against missiles and aircraft could one day draw power directly from shipboard nuclear reactors, giving warships nearly limitless defensive endurance. Unlike missile interceptors that deplete magazines, reactor-driven lasers can fire as long as the ship's generators operate. The USS Gerald R. Ford's twin reactors produce about 600 megawatts, enough electricity to power roughly 100,000 homes, exceeding the consumption of mid-sized U.S. This immense mobile power supply turns the carrier into a floating nuclear station capable of supporting next-generation weapons and sensors far from land. The Ford's construction cost reached about $12.9 billion, with another $780 million for post-commissioning trials after years of delays and more than 19,000 design changes. Much of the overrun stemmed from integrating first-of-its-kind systems and rapidly evolving combat technologies. Its reactor spaces occupy vast internal volumes surrounded by multiple containment layers, pressure vessel, reactor compartment, and outer hull, monitored constantly for radiation. Crew members working near the reactors wear dosimeters, while the Navy's nuclear training pipeline demands 2 years of academic and hands-on instruction at prototype plants, producing the world's safest record of naval reactor operation. Automation defines the Ford-class philosophy. Despite being larger than its Nimitz-class predecessors, the ship sails with 500 to 900 fewer sailors thanks to integrated controls, predictive maintenance sensors, and automated damage control networks. Certified combat ready in 2024, The carrier embarks about 90 aircraft, F-35C, Lightning IIs, Fa-18, Super Hornets, EA-18G Growlers, E-2D Hawkeyes, and MH-60 Seahawks, capable of sustaining 160 sorties a day, surging to 270 when required. 3 more Ford-class carriers, John F. Kennedy CVN-79, Enterprise CVN-80, and Doris Miller CVN-81 will follow through 2032. Each designed for 90-year lifespans adaptable to technologies yet unimagined. Displacing 100,000 tons, the Ford's 4 propellers can reverse thrust to halt the giant hull over thousands of yards, with nuclear power ensuring full maneuvering energy at any moment, without a drop of fuel burned.